Hello, and welcome to another ANSYS Workbench tutorial. In this tutorial, we're going to focus on nonlinear materials that have different tensile and compressive yield strengths, and then we're going to load these materials or the structure into the plastic deformation region. So to begin with, after opening ANSYS Workbench, the first thing I like to do is come up to my units and click on units and change them from metric down to US engineering. And so I click on that to change the units. Now I'm going to come down and double click on static structural, and that'll bring up my static structural drop down windows. So to begin with here, since we don't want to just use the default material, I'm going to double click on engineering data. And you can see as you know that structural steel is the default material. Here are the default properties for that particular material. You can see there's a tensile and compressive yield strengths, and there's tensile and compressive ultimate strengths. We can change those for the materials that we will be looking at. Over here, you can also see that you can set a temperature and then enter in these lower and upper limits of various material properties as well, so that you can analyze your model at several different operating temperatures. For what we're going to do in this tutorial, we're going to look at nonlinear materials. So I will close the plasticity window and I'll just come up and look at some of these. The first one is the physical properties, and there's not too much I'm going to change with this. These are kind of set, and in this tutorial I will not be using any of these other physical property values. You can see that these values here are simply grayed out because they are already in use. If I were to come and delete one of these, it would show up again here as a menu item that I could select. If we close this and look at linear elastic, you can see that we're using the isotropic elastic model. So coming down over here, you can see we have the isotropic elastic model already in the definition of our material. We could pick orthotropic or anisotropic or any of those that we wanted. Since we're going to be dealing with plastic and plasticity, I'm going to come to the plasticity, and you can see that I have all of these options that I can use for a plasticity model. Oftentimes you will use this multilinear isotropic hardening. So if I click on that and double click, you can see now that it is grayed out and I have the multilinear isotropic hardening. And then over here I have a tabular indicator that says, hey, these data get entered in as a table. So coming up over here to the table, you can enter the temperature, you can enter the plastic strain and stress for your stress strain curve. The thing here that you want to pay particular attention to is that this is plastic strain. So it is the net plastic strain, in that for your stress strain model for your material, you need to subtract off the elastic strain and enter in only the plastic strain with the associated stress. That's one thing that can catch you if you're not careful there. This also only lets you enter in a tensile stress strain curve. It doesn't let you enter in both a tensile and a compressive stress strain curve, so that those two may be different. And so we will need to look at changing that, and we will actually do that with ANSYS APDL commands when we open up ANSYS Mechanical. One thing that's also kind of handy here is you see the question mark that shows up here. This indicates that this particular menu item is looking for more data. And you can also see that since we've added this to the structural steel material, that coming up here, we have a question mark by our structural steel indicating again that this is looking for more data. So I'm going to come down here to the multilinear, click on it, then right click and hit delete. And now it's deleted, and you can see that I'm back to having all the information that I want to have. So oftentimes we want to add a nonlinear material. To enter a nonlinear material, what I want to do is come up here to the Engineering Data Sources tab and click on that. And this lists all the data for the materials that ANSYS has programmed into it already. So you can click on General Materials, and this will then come down here and open up all the general materials. One thing that's a little bit confusing is it opens the window based on what materials you already have selected. So since we had structural steel selected, it comes down here and highlights the structural steel. So in our table, we need to make sure that we realize we can scroll up and scroll down to see other general materials. If you continue to look at this list, we can scroll down this list as well, and you can see that you have composite materials and a bunch of other material types. We're looking particularly in this tutorial for nonlinear materials, so if I double click on General Nonlinear, you can see that it brings up these different nonlinear materials. So you can see you have structural steel, but the NL behind the structural steel implies that it is a nonlinear structural steel. Or we could do an aluminum alloy that was nonlinear. All you need to do is click on the material, then come over and click the plus, and you can see that it adds this little book. And that book implies that the data, the default data from ANSYS for the aluminum alloy nonlinear has been listed. So if we come back up to Engineering Data Sources, we can see that our aluminum alloy nonlinear has now been added, and this would be a material selection for us to use. For now, I'm going to leave the tensile and compressive strengths as these default values, and we can come back and change those later when we want. If we look at the aluminum alloy nonlinear, we can see that those values have changed, and we actually have a little bit different list here than we did for our structural steel, where we had all four of those. So under the nonlinear aluminum, we have bulk modulus, Poisson's ratio, and those things as well. We're looking at an isotropic elasticity model, and then it defaulted to bilinear isotropic hardening. So if we come up here to our plasticity model, we'll see that this bilinear isotropic hardening has been selected, and that gives us these values here. Again, we'll just leave these materials as we have them defined now, because we will do our material modification in ANSYS Mechanical so that we can have different tensile and compressive stress strain curves. So I can come up here and click on Engineering Data and close it. I'm back to my project window. I'm now ready to create my geometry and open ANSYS Mechanical, and I will go to that point. So after creating a beam in SpaceClaim and opening ANSYS Mechanical, this is what I see. This beam has a cross section of 2 inches by 6 inches, and it's 5 feet or 60 inches long. So coming over here to my project tree, I can see that my geometry is imported. If I open up my geometry, I can see that I have a system solid, If I click on that, I can come down here and see that the material that has been assigned is structural steel. I may want to change that to my nonlinear material. And so this is where I'm going to start to develop my plastic model. And the thing I want to point out here is that I'm going to show you a few different things and ways to do this and help you troubleshoot the errors and understand the errors that can be given when you do something that seems right but isn't quite right. So in this tutorial, we'll do a few things that seem to be the right approach. We'll analyze the error and then we'll correct that error. And so to begin with, to enter in a nonlinear stress strain curve, what you need to do is you come to the geometry, and I can right click on that and insert, and you can see that over here on the insert window I can insert Python code, and this can allow me to execute different ANSYS commands in mechanical. And here I can enter in commands, and these are APDL commands, and APDL is the main solving engine for ANSYS mechanical. And so we won't use the graphical user interface to input some of these material commands, but we will talk directly to the mechanical APDL software and solver. So I'll click on commands, and you can see that it brings up a new window. It simply says here that commands inserted into this file will be executed just after material property or material definitions in Prep 7. So all the material definitions have already been given. We're going to run these commands, these APDL commands, just after that. And we're going to write the code right here that will let us do that. Telling you where these commands will be executed is extremely helpful, because you might put them in a location and then actually redefine your materials, and you would end up having a linear material where you think you had a nonlinear material because you overwrote it down here in this material selection. So we'll go ahead and put the commands here for now. This down here is warning you to make sure that you're using the right units in the commands that you're going to enter. One thing that I often like to do is to write the code that I'm going to enter in a different software package such as Notepad or Word, and then cut and paste or copy and paste into here. The thing you've got to be very careful with there, though, is that sometimes Word or Notepad or whatever software you're using will put hidden commands, hidden spaces, and hidden other returns and so forth that confuse ANSYS and don't let you run. So, for example, I'm going to come to the code that I have developed in Microsoft Word, and I'm just going to paste it into here. And as we talk through this code, the /prep7 puts ANSYS into the preprocessor mode. There are three modes in ANSYS. The first is preprocessor, and that's where we develop the model. Then there's a solving mode, and then there is a post-processing mode. And you can kind of see those three modes here. This is our pre-processing, this is our solution, and this here is our post-processing. So /prep7 puts me in the preprocessor mode. Now I've come and I've defined some material properties. So MP is a MATLAB command, and you can Google this and look it up, and it will tell you the information that needs to follow this MP command. So here I'm actually going to enter in EX, which stands for the modulus of elasticity in the X direction. Mat ID is just identifying the material that I'm going to be using. And then the value for that modulus of elasticity in the X direction is this 1,3 with all the zeros. Now I'm going to define a material property for Poisson's ratio, nu xy. It's the same material as I picked up here for the modulus of elasticity, and I'm going to assign that a value of 0.3. This is not dependent upon spaces. So for example, I could come here and enter in a space after each one of those comments. It's just how I wrote the code in Word and then copied it in. The other thing that you can see is that if you click on the row of material, you can see that it tells you MP lab is the material that you want to, or the material property you want to enter. This is the mat ID, and then these are various coefficients and numbers that you can enter. And so this would be our first CO, would be this 13, and if we click on MP here, this would be 0.3. So now I'm going to come down and I'm going to build a table for my cast iron material. So TB means table, cast means I'm going to use a cast iron material. I'm using the same material ID as up here. These commas are just placeholders where I don't want to enter a value, and I want to define this as an isotropic material. I'm going to change the Poisson's ratio for when I go plastic. So in table data, it's my table 1, I'm going to change the 0.3 to 0.04. So this is changing Poisson's ratio from 0.3 in the elastic region to 0.04 when I go plastic. Now I'm going to come down and enter the values for my tensile and compressive stress strain curves. So I'm going to make a table. It's going to be uniaxial material IDs, the same as this up here. This one tells me that I'm working with my one material. This says that I have 5 values that I'm going to enter into my stress strain curve, and this tells me that it's a tensile stress strain curve. You can see down here, this is exactly the same, except for I'm going to be entering a compressive stress strain curve. You'll also note that this is true stress in PSI versus true strain. So the first value here is the temperature, TB temp. I'm setting the default temperature to 71.6, and then I enter in these values. So TB point, table point. I don't need to number those because it will automatically just run them consecutively as I have them listed. This would be my strain value, and this is my true stress value in PSI. So I have the table entered here, and I can go ahead and leave that for now, and I'm just going to leave it in this form, and we'll come back to it. So as I close this, I can close the geometry, and I can come and do a mesh. When I do my mesh, I'm going to just generate the mesh. This will likely be too coarse of a mesh for what I'm looking for. There I see my mesh, and I do want to make it finer, so I'll come down here to sizing, and on resolution I'll click here, and I'm going to increase this to the highest value of 7. Hit enter. You can see that my mesh goes pink, meaning it has changed and needs to be updated, so I'll click on update my mesh. Now it'll give me a new mesh with a lot higher mesh density, and that still looks like a reasonable mesh. It's not a very big model, and ANSYS should be able to solve that rather quickly. So now I'll come down under the static structural, and I will add some boundary conditions. So I'll come up here and click on fixed, and I'm going to fix this end of the beam. So I'll click on that face, I'll click apply, and I now have a fixed end there. So I have a cantilever beam. Now I'm going to come over to a force, and I'm going to put a force on this face. So I'll click apply, and then I enter these in terms of components. So I'll hit the drop down, go to components. I'll come to the Y, and I'll enter in a minus 5,000 pounds, enter. So I now have my model pretty well developed. I'm going to come here and look at the solution and see what I want for output. So in deformation, I'll do a total deformation. I'll do a directional deformation, and I'll come and I'll click this to be in the y-axis instead of the x-axis. I want to look at a strain. I can do an equivalent von Mises strain. Other strain options are equivalent plastic strain and equivalent total and so forth. And I'll come back and look at some of these. In terms of stress, I'll do a equivalent stress or the von Mises stress. And then I'm going to come over here to the toolbox, and I'm going to see what I have in terms of a toolbox here. And I can enter in a stress tool. And if I come over here and click on this stress tool, you can see that I have a safety factor. And so this would actually compute a safety factor for me and let me see where my material has failed. You can see that right now it's using a maximum equivalent stress theory, and its tensile yield per material is the stress limit type. And so this will let me know when I exceed the yield strength. So there's the model that I'll initially try to solve, and we'll go to that point and see what happens. So if I come here and click solve, you can see that this warning down here comes up, and I can come here and double click on this, and it comes up and says one or more unidentified characters have been detected in the command snippet, which have been replaced by underscores. So in my command snippet up here under my materials that I typed in, there are unidentified characters. So I'll click OK, and I'll come back up here to geometry and open up my commands. And the thing that you want to look at is if you click on this first row, it looks like all my commands are right in place and in good order. And there shouldn't be anything wrong with what's going on in there. But what you'll actually realize when you look at this is that these commands need to be in all capital letters. And so I will go ahead and change all of those to being in capital letters. But I wanted you to see what this error is like and how it refers you to go look at your command lines and say, hey, what's wrong with these? And this is where you also need to be careful. If you copy and paste from some other software package, you need to make sure there aren't any hidden items that would be interpreted by ANSYS and also cause you an error. So I'll pause the video, go make those changes, and come back. So now you can see I've gone in and I have exactly the same code, but I have all these commands in capital letters. I'll keep the rest of my model the same, my mesh, my boundary conditions, force, and so forth, and go ahead and try another solve. And when I do this solve, you can see that it's working on it, and I get this error. It says an unknown error occurred during solution. So I can come up here and double click on this error, and it says an unknown error occurred during solution. Check the solver output on the solution information object for possible causes. So I need to look for the solver output on the solution information. Here is my solution information, and I will go look at the solver output on that solution information. So I just click OK. I'll come over here to solution information, and I can just scroll down here until I see an error, or I can actually do a Control F and type in error, and I can take it all caps now, and type in error, and you can see that unknown table label 1, the TB command is ignored. So this is still coming back to my command code, and it says that this label 1 is unknown as to what that is. So as I can see, the unknown table label 1, the TB command is ignored. If I come back to my commands, I can look through here and see where I have a TB comma 1. And if I look at this right here, I find it. And this should actually be table data. So this should be a TB DATA command instead of just a table command. Now I have fixed that, and we can go back, and if we come down here, we can clear our errors. You can click on two messages, and there they are, and you can delete them, click on them and delete them, or you can leave them and it just lists the new ones. So now I made that change. I'm ready to come back and try a solve again. So I'll click solve. I've got green so far. I don't have any messages or anything coming up yet, and I am getting a solution down here, an indicator. So now I got all green, and I can look at my total deformation. If I orient this about the x-axis, yeah, I have a cantilevered here, bends down here, deflection gets bigger as it goes out. I can look at the equivalent stress. Yeah, this looks like a neutral axis coming in along here. One thing that is interesting to note is that I clearly have a larger stress down here on the bottom where it's red compared to up here on the top where it's still down here in this yellowish green. So I have quite a bit different stress due down here to the bottom than I do up here on the top. And that can be due to my different stress strain curves. To make sure that my analysis settings and stuff are correct, I'm going to want to increase this force. And so when I come to the force, I'm going to click on it, and I'm going to change this to minus 10,000 and click enter. And now I need to come up to my analysis settings. So under analysis settings, I'll click on this, and there's several things we want to come down here and change. Oftentimes when you're doing a nonlinear problem and you have large displacements, you need to change the number of steps. And so we'll come here, and instead of applying all the load in one step, we're going to apply it incrementally in 8 steps. So just a little bit at a time, so there's not such a huge change that ANSYS has to compensate for. The rest of these are okay. We'll come down to auto time stepping, and we're going to change that from program controlled to off. And then when we turn that off, we're able to set the number of sub-steps. And I'm going to come in here and set this number of sub-steps to something like 15. The solver type is program controlled, it's okay, all of this is okay. But when I come to large deflection, instead of having large deflection turned off, I want to turn that one on. so that now I have the ability, or ANSYS knows that there will be large deflections and it might need to take these time steps. I can look at nonlinear controls and different solvers, but this is all pretty much just program controlled, and that is fine. I can look at analysis, data management, and everything here is pretty much fine. If I want to continue the analysis and start from where this thing might fail or end, I can click none. I can click on the drop down menu here, and I can pick one of these other options. But pretty much for now, those are the settings that I need to make. You can see that I have a graph that shows up down here now, and as we solve this, we'll look at what goes on with the graph. You'll note that it goes up to 8, and this is the number of substeps that we chose. And so I'll go ahead and hit the solve on this. You can see we've got green so far. We don't have any messages so far. So you can see that it failed to solve with this higher load. You can come down here and see all these things turn pink, which give you caution. And you can see here that we're looking at our deflection. This is our deflection, and it continues to grow and grow and grow very high. So what I want to do is come back up to my solution information and do a Control F and look for error again. And when I come down here and look at the error, it says, please review output or error files. And I can just go to the next one and search through here until I find the reason for the error. And you can see that I had a number of warnings on my restart, and I'll just keep looking through here. You can see material number 2 used by element 68081 should normally have at least 1 MP or TB point. So this makes me wonder why I'm using material 2, and I do have an MP and a TB. So that gives me some concern as to what's going on there. So as you continue to look through your solution information, you can come down here and see all these warnings that cast iron tension local algorithm, NR algorithm, does not converge for material 1. So that's an indication that your stress strain curve that you have entered might be in error. And one of the more common errors for this is that you haven't gone to enough strain to let this solution converge. So what often you need to do is come back to your commands and enter in new data that will extend these two stress strain curves. So I'll do that and then come back and show you what I entered. So what I did is I came in and I added 4 more points to the tension stress strain curve, and I changed this from 5 to 9 and added 4 more points to the compressive stress strain curve as well. So I now have this stress strain curve. In my analysis settings, I have increased the number of steps up to 12. I have the number of sub-steps set at 10, and again I have large deflection on. And now I can go ahead and solve this model. So as it solves, it takes a minute, so I'll go ahead and pause. So now that we have a solution, we've got our green checks, we can come over here and look at the total deformation. The general picture looks good, our fixed end and our displaced end. Our convergence down here looks good. We converge within the first time step, and we have enough sub steps that this looks just fine. Our directional deformation, again, looks very similar, looks good. We can look at the equivalent stress, and one thing we note on the equivalent stress is that our stress is much higher here on the bottom of the beam than it is on the top, and that our neutral axis has shifted down. This is likely due to the large load that we have placed on the material and the loading that we have. We can come down here to our stress tool and look at our safety factor. We can see that our safety factor is well below 0 in this red part, and up well above 0 at the top of the beam. And that information, along with our model, ought to give us an indication that maybe something is going on wrong here, because this material has a very high yield strength in compression compared to tension, and so we would expect a higher safety factor down on the compressive side of the beam compared to the top side of the beam. So what we ought to do is come back up and look at our material. So under geometry, I'll click on SysSolid, and I can see that this has still been listed as structural steel. And so that's not the material I want. I need to make sure I'm using the right material. So I need to go back to Workbench, and under Workbench I have the materials up. If you didn't have the materials up, you double click on Engineering Data, and I can see that I have not added cast iron to my material list. So I need to click to add a material, or I can look up my data from the ANSYS website. And I can do this by clicking on Engineering Data Sources, and then my various sources come up. Under General Materials, I have gray cast iron, and I can click on that, then come and hit the plus button. I get my book indicating it has been added. I can come back up and click on Engineering Data Sources. I see gray cast iron now has been added. I can close this off, and I can see that my model here with these arrows being twisted without the green check needs to be updated. So I can right click on model and hit update, and this will update the model. You can see I now have a green check. I can come back to mechanical, and you can see that I have the material gray cast iron added there now. So I can go to geometry, system solid, and come down here to the material assignment and click that and add gray cast iron. Now I've got gray cast iron in there. I can go ahead and hit the solve button again, and this will solve fairly quickly, but I'll pause it while it solves. So I have my solution. It's a little hard to see the bottom of my solution output, so I'm going to just grab here and click and slide that down a little bit. You can see that it moved it over to that other side, and if I like that view, that's fine. If not, I can just drag it and move it down to the bottom. And you can see that you have these different icons that let you set it up in a different way. One handy button when you get your windows all mixed up is to just come here to the Home tab and then come to hit Reset Layout. If you click on Reset Layout, it brings you back to the default, and then you can move these again around as you'd like to. After that's solved, if we click on the safety factor, we note that we get an all red box with no meaning. Our equivalent stress looks fine like it did before. Stress is a lot higher on the bottom. Deformation looks good, but our safety factor, all being red, should give us cause for concern, indicating that we might not have something set right. So when that happens, what we need to do is look at how our error or our safety factor is being determined. And so if we look at our drop down, we can see that our geometry has all bodies. We're looking for a safety factor. It's based off of the last time step. Everything here looks good. If we come up to stress tool, and click on stress tool, we can see that the theory that's being used is maximum equivalent stress. This is like the von Mises stress, and if you remember from your coursework that the maximum equivalent stress is the von Mises or the distortional energy failure theory, and that requires that the tensile and compressive yield strengths be the same. And in this case, they certainly aren't the same. So I need to click on this menu and see what my options are. Here I have a more Coulomb stress, and that will let me set different compressive and tensile yield strengths. So if I click on that, now you can see that I do have the option for a tensile limit type and a compressive. If I click the drop down over here, I can set the ultimate strengths or the yield strengths as the values or a custom value. And I'll go ahead and just use the yield strengths for those and use those default settings. So now I can see I have some lightning bolts. If I come back to the solution and hit solve, it will quickly update those. Now when I click on my safety factor, I see, hey, I'm still getting a red sign. So that makes me come back and think about, well, what are my material properties? And so if I come back to Workbench and open up my engineering data again and click on my gray cast iron, I can come down here and look at my tensile yield and my compressive yield, and I can see that those are zeros. And so there's nothing there that ANSYS is able to use to determine a safety factor because I haven't entered in the strength values. So I'm going to come to the ultimate strengths and change the units from pascals to PSI. And if I change that on both of them, I can see that the ultimate strengths are close to 35,000 and 1.2 to the fifth. So I'm going to enter in a tensile yield strength in PSI. So I'll click that to PSI, and I'll click the tensile yield strength to be 25,000. And I'm going to click this to be PSI again, and on the compressive yield strength, I'm going to enter that to be 45,000. And now that I have those entered, I can come back and close my engineering data. I note again that my model needs to be updated, so I'll right click on model and then hit update, and this will update and give me a green check. I'm now ready to go down and come back to mechanical. I can see that my equivalent elastic strain changed and my safety factor changed, and those are both due to the changes in the yield strength that we just made. Now if I click solve, this will solve again quickly, and I can see that I've got a safety factor now that looks a lot more like what I'd be looking for. I can see here that my safety factor at the top and the bottom are both below 0, but that my safety factor and tension is actually shows more red than down at the bottom. And that's even based on this equivalent stress plot with a higher stress here, because my material is a lot stronger in compression than it is in tension. So even though my stress is higher on the bottom, when I look at the safety factor, it's just a little bit lower because of the strengths I've added. And now this model is starting to make a lot more sense, and I can use it to validate my beam that I wanted to model and analyze. This sums up the video, and hopefully you found it helpful. One other thing I'd like to just add on is that's really helpful is if you come to your main directory where you store your files and you click on the main file and open it up, then if you go to the DP0 sys, and this is Design Modeler, it's where you can build your model. This is engineering design. But then this is ANSYS Mechanical, and if you open that up, it has a file 0.err, and this is an error log. So if you double click on it, this lists all your warnings and errors. And it's a really handy file because it kind of takes a lot of information out of the solution and just lists the errors and helps you find them a lot more easily and a lot faster. So use your file 0.err as your error log, and it can be very helpful for you to determine what errors are going on and how to fix them.